Okay, so second theorem here today, looking with regards to our transformation matrices. It says that the columns of a transformation matrix are the images of the points 1, 0, and 0, 1, respectively. So again, the columns of a transformation matrix are the images of the points 1, 0, and 0, 1, respectively. So here's what I mean by that. Let's consider that 2 by 2 matrix there. That's my matrix T. That's my transformation matrix. Okay, and it is multiplying a point of 1, 0, which I'll call A, and the result would give me A prime for my image, right? Okay, so think, I'm going to go first row, first column, A times 1 plus B times 0. That's just going to give me a value of A, right? Then I go second row, first column, C times 1 plus D times 0. That's just going to give me C. Okay, so what we want to notice here is that the elements that were in the first column of the transformation matrix, they give me the coordinates of the image. Okay, so I'm going to state here, those two values are the image of the original point 1, 0. Okay, now likewise, in the second equation there, if I have T, let's call this B and then B prime. First row with first column, A times 0 is 0, plus B times 1 is B. Second row, first column, C times 0 is 0, plus D times 1 is D. Okay, so the coordinates end up being BD for the image B prime, and they came from the second column here. Okay, so this gives you the image of 0, 1. All right, so taking this a step further, let's say I had a transformation matrix T with the following elements: 1, -2, -1, 2. All right, just by looking at that, I can tell you that the point 1, 0 is going to transform to 1, -1 by looking at the first column. And I can tell you that the point of 0, 1 is going to transform to -2, 2. Okay, now knowing this theorem, this can help us develop some transformation matrices for different types of transformations that are pretty common. Okay, so let's consider a reflection across the line y or the or the y-axis. Excuse me, reflection across the y-axis. All right, so let's say I've got a point of 1, 0. If I reflect that across the y-axis, what's it become? Well, it comes over here and turns into -1, 0, right? Okay, so I'm going to say the point 1, 0 is transformed to -1, 0 when I reflect over the y-axis. Okay, what about the point 0, 1? Well, doesn't that remain in the same position when I reflect over the y-axis? Okay, so 0, 1 stays 0, 1. Okay, so this allows me to create a transformation matrix, T, where the point that is in red there can be used as my first column. The point that is in blue can be used for my second column. So now this 2 by 2 matrix T can be used to reflect any pre-image over the y-axis. Okay? All right, now let's do same process, but this time we want to rotate our pre-image counterclockwise 90 degrees. Okay, so draw a little picture to visualize. If I start with 1, 0, and I rotate that counterclockwise 90 degrees, that's going to rotate up to here and become 0, 1. Okay, so if I'm setting up this transformation matrix T, I know the first column should be 0, 1. Okay, what happens to 0, 1 though? When I rotate that counterclockwise 90, it's going to come here, and it's going to be at -1, 0. So now the second column of this matrix has to include -1 and 0. Questions on either of those examples? Okay. All right, one more theorem. Okay, suppose S and T are transformation matrices. Then the matrix S composed of T, you guys remember this notation from Algebra 2? It's a composition. Okay, well, normally in a composition, you insert something into a function, okay, get a result. You take that result, you plug it into the other function and evaluate with, right? So like the mark of a composition is evaluate one function, get a result, plug it into the other function, get another result. Well, we have that concept with transformations. It's like when I'm composing with transformations, I'm performing a transformation on my pre-image, getting a result, and then taking that result and performing a transformation again, right? So just like a composition. Well, this theorem is saying that the composition between S and T is going to be the same as the product matrix S times T. S times T. Okay? So let's see this with an example. I have specific values for S and T there, and I'm trying to work with the point 3, 5. Okay? So I want to find S composed of T of A, meaning I'm going to perform the transformation rule T on point A first. Then I'm going to take the result of that, whatever that image is, and I'm going to perform transformation S on that. Okay? So the way we could look at this, we could treat this like, let's do this in red actually. So we have -1, 0, 0, 1. That's for matrix S. Okay. I'm going to save that for after I multiply matrix T by my variable matrix for A. Okay, so I'm going to carry this down, save that for the next step. Okay, now matrix T times matrix A there. So first row with first column, you'll end up with a 6 plus a 0, so 6. And then second row, first column, 0 plus -5. Okay, so this would in a sense be like A prime now. Okay, so we had S, T, A. T transformed A to A prime with the coordinates now of 6, -5. And now I'll multiply that with S. I'll end up with, we could call that A double prime, -6 plus 0, or -6, and then 0 plus -5, or -5. Okay, so that would be one approach, but then this theorem says that I should be able to multiply S and T first and then find the product between that and the matrix that represents A, and I'll still end up with the same thing. Okay, so let's show it in that order. Okay, so a 2 by 2 of S multiplied by a 2 by 2 of T. That's going to create a 2 by 2, which we'll call ST. Okay, so I'll get a -2 plus a 0. I'll get a 0 plus a 0. Moving down to the second row, 0 plus another 0. And then a 0 plus a -1. Now I can multiply that by matrix A here. And that will effectively give me A double prime as well. Okay, so first row with first column, -6 plus 0. Second row with first column, 0 plus -5. All right, so showing doesn't matter what order we do it in, we can perform the transformations individually, or we can find the product of the two transformation matrices first, then multiply that with the original pre-image coordinates to get the final image coordinates. Questions there? All right, final example. Okay, so pretty much everything we've done so far within this lesson, these have been linear transformations, okay? So where the point xy is transformed to ax plus by, cx plus dy, those are called linear transformations. Why? Because these are linear in nature, okay? And we've seen that those are requiring matrix multiplication, right? Okay, well, what about the very specific type of transformation, a translation? When you translate a figure, what are you doing to the figure? Can you describe that movement? Mm-hmm. Yeah, it's just you're sliding it, right? You're moving it left or right, up or down. Okay, so think, what operation would you be using if all you're doing is trying to slide? Addition, right? This would just be matrix addition. All right, and notice I have the point xy is being transformed to x plus h, y plus k. So we're moving h units left or right, k units up or down. Okay, so all I have to do is add h to x, add k to y, and I've got my new coordinates, okay? So how would this look in terms of matrices? Well, it says describe the motion of the translation on point A of 2, -4, translating to the point 6,5, and then express it with a matrix equation. Let me start by graphing this. Okay, so 2, -4 is the original point down here. We'll call that A. 6, 5, 3, 4, 5, 6. Right here, we'll call that A prime. Okay, so obviously to move from A to A prime, we're moving right 4 units. And then from there, we're going to move 9 units up, right? So one way we could describe this, if we're speaking in terms of any point xy, so we could say the point xy becomes x plus 4, comma, y plus 9. And our equation now will be xy plus 4, 9, where 4, 9 is our transformation, or our, more specifically, our translation matrix to give us x prime, y prime. All right, and of course, I have this is just set up for a single point right now, xy, but I could make that matrix, my variable matrix, have as many columns as I want, depending on how many points I'm working with, right? So if there were 3 points I'm working with a triangle, I would just make that first one x1, y1, second column x2, y2, third column x3, y3. Okay, but then understand, if we're now matrix adding here, I can't just leave the translation matrix a 2 by 1. If I just left it like this, that sum would not be defined, right? When you are adding matrices together, they have to have equal dimensions. So this is a little redundant, but what I'd have to do is I'd have to add in 2 more columns, so I have a total of 3 columns, all being made up with elements of 4 and 9. Okay, so whatever the size is of the variable matrix representing the coordinates of your pre-image, that has to be the size of your translation matrix. Okay.